So when we talk about the buoyant force, it's a real and genuine force, and it's going to be in the opposite direction of gravity. And here's how we state the size, the magnitude of the force. The buoyant force is equal to the weight of fluid displaced. Again, the buoyant force is equal to the weight of the fluid displaced. Now, this is the standard idea about Archimedes' principle, but if you don't know who Archimedes is, what's happening is that if you have, say, a container filled with a fluid, and let's go ahead and use, say water. So there's water in our container, and you place an object in that container. The object that's in the container is displacing water. I'm not even sure where I was, but luckily we got interrupted. I don't even have a school computer. I gave mine to some other teacher who was new and didn't have one. I thought I'd get it back by now, but clearly not so much. Don't care. The buoyant force exists for a number of reasons, and we will look into part of it. But one of the simple ideas is that there is a force on the object, on all sides of it, from the fluid that's been displaced by the object. So it's, the object's pushing the fluid out of the way. The fluid wants to rush back in there and get into that space. The combination of all of this fluid trying to get back into that space is what causes there to be a buoyant force. And we'll label it F with a little b in there because it's a buoyant force. And the size of that force depends on how much of the fluid is being displaced. It's specifically about the weight of the fluid displaced. Now, again, one of the things I would hope you would have had at the ready is knowing a little bit about this. When we talk about this force on the sides of the container, we're talking about pressure. Now, in chemistry, they're a little bit elusive about what pressure was. You're supposed to be given a definition. It's like the force of a gas on the walls of its container is probably what you were taught in chemistry. So for us, we actually quantify that, which is why we call this physics. It's the force per unit area. And quite literally, newtons per meter squared. This has a special name. It's called a Pascal. You probably used kilopascals when you were dealing with this in chemistry. But a kilopascal is 1,000 pascals. You might have also used ATMs, which is atmospheres. This is using what the pressure from an atmosphere at sea level would be. We won't use that. We're going to use pascals. There's one more way you might have learned about it in chemistry, and that would have been millimeters of mercury. It's a kind of an antiquated way of talking about pressure. It's used for weather because it's a comparative measure of pressure, dealing with the barometric pressure of the atmosphere. We are going to use this straightforward measurement, pascals, which is newtons per meter squared. So there is a pressure on all sides of the object, and that causes a buoyant force. Now, the object experiences other forces, and I think this is going to be obvious. If the buoyant force is less than the weight of the object, then the object sinks. If the buoyant force is equal to the weight of the object, then it floats. Right? And that force would be zero, but that means it could float anywhere in there. And if the buoyant force is greater than the weight of the object, then the object would get buoyed to the surface. That's just what happens there. So floating is when those things are equal. So most of the time, if you've ever been in the water, you'll notice that most of you float. Not all of you, but most of you float. And if you do float, you probably float in such a way that part of you is above the water and part of you is below the water. It's not an accident. The settling occurs when just the right amount of you is below the water, so that the buoyant force upwards is equal to the weight downwards. Now, when we talk about measuring this, remember it's the weight of fluid displaced. Displacement is volume. And when we talk about displacement, we're talking about volume. But the weight of the fluid is the mass of the fluid times g. So to figure out how to put this properly, what we do is simple. We remember something from chemistry. Again, painful as it is, we use density. For us, the symbol for density is lowercase rho. It's like a P without the hunchback. So you just write it as like one continuous little thing like that, lowercase rho. And this is going to be mass per unit volume. If you do a little arithmetic, you'll see that mass equals density times volume. That means the buoyant force will be rho times volume times g, where this is the volume displaced and rho is the fluid's, not the object, the fluid's density. Alrighty.